Einstein dreamed of finding a general and uniform theory of the field, a simple equation that could explain any fundamental process in nature, from the union of atoms to the rotating movement of the galaxies. Today science is very close to perform Einstein's dream. The nucleus of the atom offers us the evidence of an elegant underlying simplicity in the frantic diversity of the universe. Today new uniform theories are appearing that reveal indications of that fundamental simplicity. The 1984 Nobel Physics Prize was granted by certain experiments that confirmed these new theories. Experiment and theory indicate that the universe began in a perfect state of simplicity. The evidence of this was consumed with the heat of the great explosion at the beginning of the times. We have approximate knowledge of the history of the universe from 1/100th of a second after the great explosion. Something extraordinary that I can say this, and it is even more extraordinary that I can say without some men with white coat coming and they will take me out of here. Part of the story we have specified with enough approach because fossils and vestiges of the past have been left that tell us that our theory is true. Cosmology somehow provides a kind of test field for any of the theories about elementary physical particles. We cannot observe the primitive universe, but its consequences in the current universe. What is that? I could not define it. It is cold, it is impersonal, it is the machine, if you want, that you have created us. With this what I mean is the following. Until the last atom of our body was in a time inside a star. In that sense, we are all brothers. To know the atom we must know the universe. And to know the universe we must know the atom. In a confluence of the big and the small that Einstein's heart would have rejected, the search for simplicity faces science with the eternal enigma of creation. The creation of the universe. First part, the micromundo. Thank you to watch the video. When I was a child, I used to bring me on my telescope to the seashore, I pointed to heaven and watched what I thought it was the universe. I had read in the astronomy books that what we see in the sky is the past. The Russian mountain, for example, is a group of stars to 75 light-years away. This means that the light of the stars of the Russian mountain takes 75 years to travel through space until we reach our solar system. If one is lucky enough to turn 75, he can see the roller coaster as it was the day of his birth. This group of stars is further. It is in the constellation of Hercules, 27 light-years. Which means that we see it as it was 27 years ago, when there was no human city about the face of the earth and the arc and arrow had not yet been invented. A way of studying the history of the universe is to observe the outer space. But the universe after all is not just the stars and galaxies of outer space. It is also here in our land. We live in the universe. And everyday objects are full of signs of cosmic history. Each stone of a beach is a galaxy of atoms. And those atoms have a story that goes back beyond the history of the earth. Before the formation of the Earth, those atoms were drifting in interstellar space. Before that, some of them would be part of eldest stars. The subatomic particles that constitute those atoms could find their origin by going back 15 million years ago until the beginning of the times. In this program we will explore the history and origin of the universe. We will look up to the tiny world of subatomic particles and raise it to the cosmological borders of space and time. Our hope is to learn something about how things became what they are. Indices to try to solve this enigma are there everywhere around us. Sharpation of skyscrapers in the district of Wall Street in the lower Manhattan. More than 2 kilometers from here to the north there are no high buildings. And later, in the central Manhattan, the skyscrapers arise again. It is a natural development. Its destination was marked hundreds of millions of years, when the molten lava flowed through the Hudson River Valley and the rock bed on which the city rise was folded due to certain geological processes. The result was a couple of underground mountains. As the skyscrapers have to be based on rock beds, the sinuous shape of the Manhattan horizon line traces the contours of an underground mountain chain here where we begin our exploration of the kingdom of the atom and the abysses of the past. Times Square is the most unnatural that one can imagine and still must also a large structure to its natural history. The planetary processes that gave it their form are usually too slow so that we can appreciate them with the man's time scale. But imagine a trip to the past at an accelerated rhythm. So we could see how Times Square took. Let's see it. We are going to walk towards the past at a pace of a century by step. A century is a century. Times Square, then known as Longacre Square, was a dark and dangerous place, a paradise for the robbers. Its transformation in the Gran Via Blanca, a more bright and consequently safer place, was due to the applied physics of Thomas Alva Edison and its invention, the electric light. 200 years before that, Times Square were tillage lands. The Hopper family cultivated choles on Broadway and on 51 Street. How many steps further back in the past and Broadway was an Indian path? Only 70 steps back 7,000 years ago, and Manhattan was still discovered by the Indians. A little over 100 steps and we have reached the era of the mastodon. The mastodons graze in a time here, in Central Park. Only 150 steps are enough to place us in the last glacial period, when Manhattan was buried under a large layer of ice more than 300 meters thick. This rolled song is what geologists call a glacial erratic. He was dragged here by the ice mass in his advance. And you can still see how these rocks were polished by the glacier in its path to the south. But these rocks are millions of years. To reach that point of the past to the rhythm of a century by step, we would have to walk towards the North Pole. And the land is billions of years. To get so far in time, the whole world should be turned around. Scientists handle great figures like those using what they call exponential. For example, powers of 10. 10 elevated to the second power is 10 times 10, that is, 100. 10 elevated to the third power is 10 times the above, that is, 1,000. This time we imagine that we could walk towards the abysses of the past exponentially, so that every step we take to the past was 10 times the time traveled by the previous step. The chasms of time. Oh, land, what changes you have witnessed. Where today the streets would reign in a time the calm of the ocean. The hills are shadows and change again and nothing remains. The solid lands are dissolved as mist, as clouds are molded and disappear. The earth is old, but older are the atoms that the earth is composed, and the air, and you and me and this tree. And we can investigate the abysses of cosmic history by observing nature at an atomic and subatomic scale. And the subatomic scale, who closer we scrutinize the universe of the very small, greater evidence we find of the past. The flowers of this tree are young, its shape and color are the product of genes older than the same plant. The genes are forming successively on molecules of the deoxyribonucleic acid or DNA. The molecules become visible with an increase of 10 million times their size. Each is an accumulated genetic information library throughout the history of the evolution of life on Earth. Being even more, we can see the carbon atoms that the DNA molecules are composed. They are even older than the same land. The external limits of the atom are patrolled by a cortex of negatively loaded particles, the electrons. We attach the most internal layer of the electron bark of the carbon atom. We approach one of the most antiguous and magnificent structures of nature, the nucleus of the atom. The core is composed of protons, colored here of orange to indicate its positive electric charge, and other electrically neutral particles, the neutrons. These nuclear particles are formed in turn by trios of even older and basic particles, the quarks. We have reached the field of nuclear forces. The weak force intervenes in the process of radioactive disintegration, while the strong force unites the quarks, interwoven energy networks in shapes that we call matter. Most of what we know about the subatomic particles has been discovered accelerating the particles at high speed, making them hit later and studying the remains that emerge. A physicist compared the process with making two elegant Swiss watches against each other and then trying to find out how they were designed by studying the tooth plates and tiny screws that would jump through the air. This is not the most subtle or elegant method in the world again, but it works. This was the first particle accelerator in the world. He used principles that are still in use. The positively charged particles, the protons, were injected into this small ring where they were subjected to a powerful electromagnetic field. As protons are positively charged, they are attracted to the negative part of the field. Then the polarity of the magnetic field is reversed by making the protons hurry here. Repeating the process, you can get them at high speed until moving spiral towards the end of the ring finally collide with this objective. This prototype was manufactured in Berkeley, California, in the year 1930, provided its inventors a scholarship of $500. With that money they built a second accelerator, twice as large. This was followed by an even larger third party. Particle accelerators are increasingly and larger. The greatest thing is the accelerator, smaller is the scale at which they can test the fundamental structures of nature. And I find myself in the middle of one of the largest particle accelerators in the world. It is about Fermilab in the plains of Illinois. It works very similar to the first accelerator, using electromagnetic energy to rotate the particles around the ring. But the ring is now much greater. In Fermilab it has 3,500 meters of circumference. In a narrower tunnel than a buried firefighter hose underground, the particles accelerate until close to the speed of light and then collide with a preferred target. The resulting explosions recorded in detectors such as this reveal a wide variety of subatomic particles that interact through four fundamental forces. Gravity, electromagnetism, and weak and strong nuclear forces. According to modern physics, particles and forces are responsible for all events in our world, from the most exotic to everyday. And here's Steve Bosco. Today is a magnificent day for baseball. Thanks to you. The weak nuclear force, the sun is busy releasing energy so that the nuclei of the atoms transform it into 22 pleasant degrees here in the Tadjar Stadium. The pitcher is already at the base and everything is ready to start. It has been a magnificent blow. Without a doubt, Biff, but the force of gravity of the Earth has deformed so much the space that it seems that it will go outside. Yes, he took it. Well, it's not exactly that I took it. It is rather that the electromagnetic field formed by the atoms of its glove has surrounded the electromagnetic field of the ball. Well, whatever you say. Foot, well, let's see, who comes now? It seems that it is Reggie. The pitcher looks waiting for the signal. He has sent the ball outside. He has succeeded. A complete career. And Big Bar says goodbye to you until next day. Big Bar tells them until next time, and Steve Bosco in his third attempt and losing at home. Baseball ball and the bat are mostly empty space. Its solidity is an illusion created by the field of electromagnetic force that keeps the atoms together. Vista at the subatomic level, a complete race begins with the exchange between the atoms of the bat and the atoms of the ball. The ball is repelled and moves away. We blame the merit of the full race to the batter, but the responsible fundamental force is electromagnetism. Infinite in its reach, it is electromagnetism that brings us the light of the sun and the stars. Weak nuclear force helps to enhance the sun and preside over the phenomenon of nuclear disintegration. In the nucleus of each atom, huge amounts of energy are stored. Some nuclei are unstable and cannot retain their energy forever. When they disintegrate, it is the weak force that the particles called weak bosons carry that governs the process. Strong nuclear force unites quarks to form protons and neutrons. Without it there would be no atoms and the universe would be a confusion. The strong force is covered by particles to which physicists call gluons because they act as the most perfect glue imaginable. Gravity, the force of universal attraction of all solid particles with each other, is the weakest of the four forces. But gravity has an infinite scope and always attracts, never repels. This resolved insistence of gravitation makes it able to maintain the balance between the planets, the stars, and the galaxies. But why are there four forces? And why do they differ so deeply from nature? Einstein tried in vain to find an answer to this question. He sought what he called a simplified and lucid image of the world, a simple principle that explained the incomprehensible differences between the forces and the wide variety of particles. What really interests me, he said, is if God had an alternative in the creation of the universe. He failed in his attempt, but never lost the faith in which, as he said, God is subtle, but not malicious. That nature, although difficult to understand, should be at its root, deep down, simple and beautiful. Albert Einstein spent the last years of his life in this office of the Institute of Advanced Studies of Princeton, New Jersey, working in the search for a unitary theory of the forces of nature. He did not find it. The equations were unfinished on the board the day he died. Today the equations have a very different appearance and pass through curious names that Einstein never heard speak as supergravity and supersymmetry, but its objective is the same. Reunir in a whole disparate elements of physics. Physics today is a job work. There are theories that explain each of the four fundamental forces and do it wonderfully well. They can predict the behavior of an electron moving away in a spiral trajectory of a galaxy after their explosion, or the behavior of these photons that arrive from the sun. But they have little to say about why the forces of nature differ so curiously. Why, for example, there is a negative electric charge and another positive one, but it does not exist, for what we know so far, a negative gravity. Why do weak and strong forces work only within the nucleus of the atom while the force of gravity and electromagnetism are of infinite reach? The search for simplicity, the hope of identifying the fundamental force or the elementary particle of matter, is a constant in the history of physics since the days of ancient Greece. Atomic theory was already an old idea when Plato debated with his disciple Aristotle. Aristotle proposed that there were two fundamental forces that he called lightly, the tendency of light substances to rise, and gravity, the tendency of heavy objects to fall. The Roman poet Lucretio popularized atomic theory. Beautiful is the world created by atoms. A wedding ring becomes fine over the years. And yet we do not see gold points starting from the ring. Because gold is made of tiny atoms. With the spiritualism of the Middle Ages, the atomic theory considered as materialistic was forgotten. To emerge again alone in the era of Isaac Newton, who saw the world as composed of atoms ordered by the force of gravity. The universe is like a perfect machine, and the force of gravity that maintained it has its orbits to the moon and the planets. In the following centuries, the experiments of Robert Boyle, John Dalton and others revealed that, as Ernest Rutherford said, the atom is a complex aggregate, not a simple entity. Rutherford discovered positively loaded particles, the protons, in the nucleus of the atom. And James Chadwick discovered those of neutral load, the neutrons. James Clerk Muswell, in the first modern unitary theory, showed that electricity is nothing but an aspect of electromagnetic force. For a while it was thought that there were only two fundamental forces, electromagnetism and gravity. But the force scheme was complicated when Hideki Yukawa, Enrico Fermi and others identified two other forces not previously detected that acted within the limits of the atom nucleus, the strong and weak nuclear forces. With the 20th century, the identification not only of two new forces came, but also of many more particles. Einstein showed that the same energy consists of particles, the among how many. Wolfgang Pauli discovered a strange particle called neutrino, and the existence of the even strangely antimatter was formulated by Paul Dirac. The list continued to increase. There were ins and muons and pions. Fermi said, "If I could retain the name of all those particles, it would have been botanist." The hopes of finding a basic elementary particle of matter arose again when Murray Gell-Mann suggested that protons and neutrons are formed by even smaller particles he called quarks. The concept of force was also simplified when Sheldon Glashow, Abdussalam and Steven Weinberg demonstrated that electromagnetism and weak force are aspects of a simple force, the weak electroforce. The experiments carried out by Simon van der Meer and Carlo Rubbia confirmed the electrodiable theory. This was followed by more ambitious general and supergeneral theories, and in the mid-80s the hopes that physics could be very close to reaching a definitive unitary theory were very high. Finding a simple equation capable of explaining the struggle of quarks and stars. The problem we face now is that the standard model, the standard scheme, is very elegant, is very powerful, explains many things, but it is not complete, it has some gaps. And one of his great defects is difficult to explain. It is an aesthetic defect. It is too complicated. It has too many arbitrary parameters. We cannot imagine the creator by acting 20 buttons to establish 20 parameters and create the universe as we know it. Since the Greeks began on this path of understanding atoms, the basic elements of the entire universe, we have had the prejudice that there must be something simple under all this. And 6 quarks, and 6 leptons, and its antiparticles, and that they are of different color and with different load, it is too complicated. And there is a deep feeling that the picture is not beautiful. And that search for beauty and simplicity and symmetry has always been an infallible constant, an indicator of how you should work in physics. We have not yet touched back. But as we approach him we remember insinuations of a beautiful underlying theory of beauty we can only intuit at the present time. We do not know that it is true, we do not know that there is a beautiful underlying theory, we do not know if as a species we are intelligent enough to discover what is. But if we do not presume that there is a wonderful theory, we will never discover it. In my opinion, there must be at the bottom of all this a non-coach, not a totally simple equation, but a totally simple idea, and for me, that idea, when we finally discover it, will be so convincing, so inevitable, so beautiful, that which we will tell ourselves, it could not have been otherwise. The uniform theories suggest that nature would function more simply under conditions of extremely high energy levels. Let's see electromagnetism and weak nuclear force. At normal energy levels they seem very different. Electromagnetism is transmitted by photons. Photons are light particles and can travel huge distances. But weak force is something else. It is transmitted by weak bosons. These are heavy and can only travel short distances before exhausting and disintegrating. That is why the weak force is limited in its reach to the nucleus of the atom. But theories say that the situation could change if we managed to raise heat. Fed by environmental energy, a new particle called Z would appear, which would be able to unite electromagnetism and weak nuclear force in a single force. In this computer simulation we will see how a Z particle integrates and combines again to form a photon carrier of electromagnetism. The photon in turn disintegrates to form a pair of weak bosons carriers of the weak force. And the bosons are transformed again into a zeta particle. What were previously two forces, now is one, the electrodiable force. A way to test this theory was to look for Z particles. Like the salamanders, mythological creatures that dwelt in the fire, the Z particles would be developed only under conditions of extremely high levels of energy. The current universe is too cold so that the Z particles will last a long time. They would find even the interior of a supergiant star. When the electrodiable theory predicted for the first time that there should be such a thing as a Z particle, no laboratory of the world could gather enough heat to prove that prediction. And it was not until 1983 that science managed to light a spark hot enough to make particle Z appear if it existed. It happened in a laboratory here, on the Franco-Subtle border. The place was CERN, an international laboratory jointly administered by 13 European nations. Like other giant particle accelerators, CERN consumes as much electricity as a small city, but does not manufacture anything. The 6,000 people who work here are occupied in pure research. Thank you to watch the video. It all starts here. Accelerated particles are protons. They are easy to get. There is at least one proton in the core of every atom of the universe, and they are economical. These hydrogen bottles contain the CERN accelerator proton's supply for a whole year. LGAS emits in infinitesimally small puffs through these computer-controlled valves and ascends through this duct. The accelerator header. These tiny gas portions contain as many protons as stars are on the Milky Way. This tenacious and old generator produces about 1 million volts. The energy is used to create an electromagnetic field in this camera. In the field, the negatively loaded electrons that revolve around the nucleus of each hydrogen atom are torn, leaving the proton positively loaded positively. The electrons are left behind and the protons rush into the main accelerator. For years, scientists have accelerated protons in the giant ring of CERN, making them collide with motionless objectives. But now, for the first time, it is the antiprotons, strange particles identical to the protons, but of opposite load, then bicar and stored in the antimatter collector. When matter stumbles with antimatter, the result is the mutual annihilation. The impact of a proton and an antiproton releases during a minimum fraction of second plus energy than that produced by all the electric power plants of the world. Subatomic particles, they detach from that tiny explosion and are collected in the onion skin layers of this gigantic particle detector. The 28th of May 1983 indications of a Z particle between the waste emitted by a proton and antiproton collision were detected. The electrodiable theory was confirmed. Carlos Blond, of CERN, shared the 1984 Nobel Physics Prize for having conceived the idea of colliding the subject with the antimatter. What we are actually doing here is to cause small explosions. We concentrate on a very small volume of space and for a very short period of time enough energy to reproduce, so to speak, on a very modest scale, which was the true state of things in the universe as a whole. The greatest progress of science was made, I believe, by Galileo Galilei, when he brought experimental science to his just level of importance. And I also believe that to a great extent our scientific progress is due to experimental science. And, I do not say it because he is an experimental scientist, but because I believe that the final verdict is always the last word has the physical phenomenon. After the success of the electrodiable theory, the scientists threw themselves to compose the so-called unitary general theories. These theories say that at higher levels of energy, 3 of the 4 forces would function as one force. And again it is theorized that a new exotic particle would be in charge of the work of unification, the so-called particle X. As we see, a gluon carrier of the strong nuclear force hits an X particle and transforms into photon bearer of electromagnetism. Health. A gluon hitting an X particle X can also be transformed into a weak boson carrier of the weak force. Energy particles live in a borrowed time. They meet between the energy dispersed in a vacuum and then disintegrate and cease to exist again. Uniform theories make the amazing prediction that not only energy, but also matter can be temporary. The great uniform theories paint with more intense colors the old lesson that birth implies death. It is the last chapter of a scientific saga that began here, in Venice, 378 years ago. The 25th of August 1609, Galileo headed a procession of Venetian senators that, crossing the square, went up to the top of that tower to look at the top of that tower to look at the top of that tower. Galileo was a professor at the University of Padua at that time. He was a very respected teacher. Students went to their classes. He had published a couple of good books, but his contract was about to expire and had not gathered enough money to continue investigating. He needed something to drive his career and found him, the telescope. The senators were impressed and guaranteed Galileo a fixed position as a teacher. They helped him financially and took care of telescopes to see ships in the sea. But Galileo tried his telescopes in the sky, and those observations convinced him that the heavens were as solid and changing as the earth. Galileo's observations provided the evidence that stars and other planets are worlds like ours, composed of the same elements, and that they behave according to the same physical laws, as the world of big and small handed their hand. And that they linked to Earth with the universe. The Venetians understood that nothing in the earth lasts eternally. They were citizens of a republic literally lifted on moving sands and sustained by the risky maritime trade business. But they thought that the stars, at least, were immutable. Galileo's works changed that, introducing into science the idea that the Earth is part of the universe. He laid the scene for the subsequent discovery that even the stars also live and die. From the times of Galileo, the new telescopes have observed the exterior space to scales in which Galileo never dreamed, and particle accelerators have scrutinized the world of the small. And everywhere change has been found. If uniform general theories are true, not even atoms live forever. The city where Galileo glimpsed indications of the mortality of the skies is in danger. Venice sinks. Its streets are flooded with winter rains. The city will not be able to live forever. But that is not alone, nor will the sun. Even the other stars are the atoms that are composed. Kamioka, Japan. Aki, in a lead mine, an experiment is carried out to find out if the protons are mortal. To minimize the interference caused by the high-energy particles that reach us from space, the experiment is carried out at a depth of about 3,000 meters underground. Uniform theories predict that the ordinary proton lasts many billions of years and that gathering a huge amount of protons, scientists can demonstrate those theories in the course of a year or two of careful observation. And that is what is being done here. A pit equipped with sensitive detectors has been excavated and then filled with 660 tons of pure water. If a proton of any of the billions of water molecules of the tank disintegrate, it would send a luminous flash indicator. The computers, monitoring that luminous flash, would communicate the news to the scientific expectants. If the results are positive, the experiment would confirm a disturbing hypothesis that all the subject of the universe is a passenger whim, more stage in the endless dance of energy. If electromagnetism and weak nuclear force are united high levels of energy, they are working on the attempt to solve that enigma. Stephen Hawking is among the most prominent physicists in the world, despite suffering for more than 20 years a progressive disease of the central nervous system that has paralyzed and left incapacitated to speak. Hawking is in POC of the chair Isaac Newton as a professor of mathematics at the University of Cambridge. During a seminar held in Caltech, his words were interpreted by a former physical student specialized in supersymmetry, Nick Warner. The theme of Hawking exposure, the childhood of the universe. The conditions of the borders of the universe are the universe. No, it has no borders. It sounds quite zen, right? What Stephen means with this that spatial time something compact, something four-dimensional. Something. This is a general four-dimensional multiple. A four-dimensional compaction, a certain metric on the surface and also some fields of phi matter on the surface. I must then understand that you intend that the effect of effective unification of a John Mills or super John Mills theory is as low as 10 elevated to the 14th power, that is, m can be something else. It can be something else. But in any case, the m is the characteristic mass of the physics responsible for evolution. Generates. It is the constant of cosmological inflation. Stephen wants to add that you can also explain that with this you could also explain the arrow of time. But believe that it would take much more time than we have. That is all. 9 laboratory can produce the energy with which the 4 forces would act as one. Only the fires of Genesis were burning enough for that. The search for simplicity in the atom field leads us to the field of galaxies and goes back to the beginning of time. We live in a great spiral galaxy we call the Milky Way. Astronomers call it the local group, and the local group is part of the constellation of Virgo, a galaxy's archipelago that extends along a space of 100 million light-years. The galaxies move away from each other as the universe expands. In a computer simulation, based on astronomical observations, we are witnessing something before never seen by the human eye. The prophesied dispersion of Virgo's constellation because of the expansion of the universe in the course of the next 50 billion years. That is, and m. The expansion of the universe was predicted by the general theory of Einstein's relativity, published in 1915. But the idea seemed so extravagant that Einstein himself rejected it. He had a strange term in the field equations to try to make his universe remain motionless. Later Einstein would describe this modification of the theory as the greatest error of my career. Later, in the year 1929, the American astronomer Aaron Hubble, who did not know the prediction of the theory of relativity, discovered that the universe in effect expands. Einstein and Hubble they met in California in 1931 and celebrated what Hubble would have discovered with the telescope what Einstein's mind had conceived. Astronomer Alan Sandage, former Hubble student, has dedicated much of his career to study the expansion of the universe. The idea is that the space itself expands leading to galaxies. The expansion creates the space. The crucial analogy presented for the first time by Eddington in 1930, a year after Hubble had announced the expansion. It is that the fact can be conceptualized using the surface of a globe. Points are painted on the surface of a balloon and inflates. No, we place any of the points. It seems that then, we are the center and that the other points move away. Now we let the balloon escape and observe what the points do. They are approaching, and if we got all the air out of a perfect balloon, the same surface would stay nothing. All points would meet in the same place, so every point is the center of expansion. Always talk about this, the same question arises. Is it possible to find the center of expansion? Any point is the center. There is no center at the beginning. Everything was at one point and every point and all time were identical in the beginning of the times. Observatory of Monte Palomar in Southern California. I am sitting in a time machine in a way, an instrument capable of directly observing the past. On the end of this tube, well below me, there is a polished concave mirror that can collect as much light from the stars as the eyes of a whole community of 20 people. The light is reflected so far. Through this tiny window you can see the space at distances of thousands of light years and look at the past to billions of years of the cosmic history. Thanks for watching the video. You can collect quite old light with a telescope as large as the 5-meter Palomar opening reflector. This image that now comes to us is from a galaxy to 40 million light years away. That means that we are seeing it as it was 40 million years ago. It seems a lot of time, but it is just a fraction of 1% of the time elapsed since the beginning of the expansion of the universe. If we would like to realize our position in cosmic history, we could draw a line that would represent the time, starting from the Great Explosion, the beginning of time, as we understand it, and taking it up to about 15 billion light years more or less until the present moment. Here we are in a galaxy today, and we could draw a vertical axis that will represent the space. We can only contemplate the events whose light, crossing the space, has had time to reach us. We can represent this by drawing what scientists call a cone of light. The angle formed by the sides of the cone is defined by the speed of light, the highest speed that this information can travel, as we know. A galaxy like this, 40 million light years away, is right here, in our neighborhood. And in the same way, all the other galaxies that we can see clearly are very close within the cosmic scheme. If we look beyond, the galaxies become very weak. Let's see if we can obtain here a system of galaxies. Each of these tiny blurred points so small that they may find it difficult to see them, each of them is a sovereign galaxy of about hundreds of billions of more or less stars and a countless number of planetas. But these galaxies are so far that existing telescopes cannot capture them very clearly, not even this 5 meters from Mount Palomar. The greatest distance to which we can see the galaxies in the absolute maximum is half of the life of the universe. Beyond that, they become too weak so we can see them with existing telescopes. But fortunately, the primitive universe seems to have been inhabited by some objects called quasars. The quasars, which may have been the nuclei of young galaxies that cross a phase of violent youth and that are so bright, shine so intensely that we can see them at distances much greater than we can see the galaxies. Seeing if we can get the image of a quasar. This is so far that its light has been distorted by a galaxy that interposes between us and the quasar, and the result is a double image. These 2 points are actually a single quasarchy. Light has traveled so much and for so long that we see it is and as it was when the universe had less than 5 billion years. When the universe had less than a third of its current size and age. Quasars are so brilliant that thousands of them have been detected with the telescopes on Earth. And in fact we could see them at even greater distances if there were, but at such distances, 15 billion light years, nor the Palomar telescope, nor any other great telescope in the world find any quasar. The explanation seems to be that we are entering a time of the past in which the universe was so young that the stars, the galaxies and the quasars had not yet had the opportunity to organize independently of the primitive matter and begin to shine. But that in the past, a long time ago, there was a time of darkness, and yet, even before that, it is possible to see another form of energy. The energy produced by the explosion that began the expansion of the universe. The energy of the Big Bang or Great Explosion. This energy permeates the universe, but has been so diminished by the expansion of this that has gone from wavelengths visible to radio waves, and this cosmic history radiation, as it has been called, can be detected by means of a sophisticated radio. OSI is lucky, using a current television apparatus. Any television apparatus coupled to an antenna can detect the old cosmic background photons. To see them, put the level of brightness to a minimum and tune in an empty channel. No, not, please, when our program ends. 1% of the snow points that you will see on the screen are photons released by the Great Explosion. Universe childhood relics, particles that have been wandering through space since before the first stars and galaxies were born. The legacy of the Big Bang is still with us. The heat released by the sun and the other stars represents only a fraction of the energy stored in the nuclei of the atoms at the beginning of the times. It was then, when the universe was still bathed in fire, when nature could have functioned simple and wonderful, that is intuited through uniform theories. We have seen, observing nature on a subatomic scale, that the structures of matter and energy and even the nature of the force, the fundamental ones that are supposed to govern their behavior in the universe, would be simpler under extremely high energy levels. And we have seen through the observation of large-scale nature in the universe of expanding galaxies that the universe began precisely in such a high level of energy. Uniting these two lines of research, the scientists have managed to draw the wide profiles of cosmic history. From the first fraction of a second immediately after the Big Bang to this day. We do not know all the details of this story, of course, at all. There are lagoons. Much of what has been conjectured is doubtful, distorted, or simply wrong. But even at this early stage of research, it is possible to discern greatness and beauty and the extraordinary explanatory power of what is ultimately the fundamental history of history, the history of the universe. The story of how a simple energy core has been able to become everything that exists today. To examine the story of Genesis and the evolution in detail, suppose that the steps that take us to the tower of this old lighthouse could take us to the past of cosmic history, so that we could examine each thread of the great tapestry of time. Let us imagine that each of these lighthouse windows will appear to an earlier era in cosmic history. So that the first window showed us the universe as it was when it only had 1 billion light years. And that every step we rose from the stairs from here would return to when the universe had a tenth of its previous age in the previous step, until it reached only 100 million years after the great explosion, then 10 million, 1 million, and so on. Walking at that pace, very soon we will have reached the first second of the time. And that is very important because many things happened during that first second. Our galaxy, as well as all the other galaxies we know, formed during the first billion years of the expansion of the universe, when the fundamental gas it was still dense enough to condense, forming stars and galaxies. We do not know all the concrete details of the formation of galaxies, much less, but we believe that we have a fairly approximate image of what the Milky Way was like at first. Here it is. These first generations of stars were composed almost entirely of hydrogen and helium. There has been intelligent life in those early days of the universe. The periodic table placed on the wall of the school's chemistry class would have had only two paintings, the hydrogen and that of the helium. Once the universe had been expanding for about 1 million years, its density had decreased enough for photons to fly freely through space without continuously colliding with other particles. The result was the birth of light. This was also the date of the birth of the first atoms. Free at the end of photons' harassment, electrons could enter orbit around atomic nuclei. An electron turning around a proton gives us a hydrogen atom, the simplest and most abundant of the elements. Two electrons orbiting a couple of protons plus a couple of neutrons gives us a beautiful helium atom. But these helium nuclei were already on hand. That was the first moment in which things had cooled enough so that protons and neutrons could join to form atom cores that were not constantly destroyed by the omnipresent heat. Now, for the first time, protons and neutrons are able to join thanks to the strong nuclear force. They tend to form thirds, and the thirds are combined to form an unstable nucleus. 2 of the extra outstanding protons are expelled, and the result is a stable core of helium. This complicated coupling ritual seems to have been very popular in the early stages. So popular that theorists estimate that approximately a quarter of all the subject of the universe had to condense in heliogas. And when astronomers study the chemical composition of the universe in general today, they find that a quarter approximately is him. They are this type of confirmations of the theories for experimentation that lead scientists to think that they really understand something about how helium atoms were formed in the Big Bang fires. We now enter very remote times. When the universe had only a second, the heat was so intense that it even won the strong nuclear force. That is the force that keeps quarks together to form protons and neutrons. From here back, not even such fundamental structures such as protons and neutrons can exist, and the universe is a free quark soup. A tenth of second, 100th of second after the beginning of the times. The universe is now so dense that even neutrinos, subatomic particles so meager that they can cross a solid lead block of 1 billion kilometers without stumbling with anything. Even neutrinos, we said, are currently contained in universal broth of matter and energy. A 10,000th of second after the beginning, the heat was intense enough for electromagnetic and weak forces to be even joined and functioned as a single unitary force, the electrodiable force. Z particles Z could arise in abundance with the heat of the electrodiable era. The weak bosons and photons acted alternately and the universe was governed not by 4 forces but by 3. When the universe had only a tiny fraction of second age, approximately 10 elevated to less 35 seconds, to be more exact, it is believed that the electrodiable force was not yet separated from the strong nuclear force. During a brief moment, the natural simplicity conceived by uniform general theories was a reality. The exotic X particles and the quarks furrowed the subnuclear seas. Gluons, protons and weak bosons danced alternately. Thus, only 2 forces operated in the most primitive universe, severity and electronuclear force or unified general force, as it is called. But it is possible that even before, in the history of the universe, things were even simpler. We have reached the first moment of time. The fraction of second elapsed since the universe began its expansion is so small that it has no name. To express it, a decimal should be written and then a row of 40 and so many zeros. The universe, everything that exists or can exist, was contained, we believe, at this time, in a simple spark of rapid expansion energy, but even smaller than the core of an atom and governed by a simple primordial law. If we knew what happened at that time, we could finally understand the relations between the laws of nature and between space and time and between matter and energy. But we still do not know. We lack a theory that can explain how nature would have behaved under these extreme circumstances. There are many who seek that theory. Some believe that the key is in a kind of quantum severity, for which they have called super-uniform theory and supersymmetric theory. And of course, we do not know what that theory will say, but whoever is left with that theory will be the first man who has peeked into the threshold of creation. Probably the most fundamental question that can be asked about the universe is, what did he make it start? What is the origin of the moment of creation? And that is probably the most difficult to answer because in cosmology the way to rebuild the history of the universe is passing the film back. And to pass the film back, the laws of physics are used. The physical laws that we know in the present are probably good enough to place ourselves in the past to only 10 raised to less 43 seconds of the explosion or the moment of creation. That is a lot, but to go back even more we need moreness of gravity. I suspect that we can always find ourselves in that situation, that to go back a minimum fraction of seconds we need some knowledge that we do not have, and I think it can spend a lot of time, if it happens, before we can answer the question that we would all like to know: what caused creation? It can be that the universe has had a beginning. It can be spatial time for a closed surface without limits, similar to the surface of the Earth, but with 2 more dimensions. If the idea that spatial time is finite but unlimited, it is correct. That the Great Explosion is like the North Pole of the Earth. Asked what happened before the Big Bang as little as I asked on the surface of the Earth 1.5 kilometers to the North Pole, a meaningless question. If there was the fact of creation, there had to be a cause. This was the thought of St. Thomas Aquinas, one of the 5 ways to demonstrate the existence of God. If the first effect is found, you have approached the first cause, and if you find the first cause, and if you find the first cause, and if you find it for the first cause, what do astronomers say? As an astronomer, nothing can be said, except that this is a miracle that looks like a casi sobrenatural. An event that has crossed the horizon and has entered science through the Big Bang. Can you go in the opposite direction, cross to the other side of the barrier and finally give the answer? Why has something emerged from nothing? No, you can't. Science cannot, but there is still an incredible mystery. Why is there anything in place? The ancient Chinese conceived being as arising from their opposite, not being. Nothing wrote, produced the universe, and space, and time. Prehistoric myths painted Genesis in biological terms. The primitive God became a light blue egg. In the Judeo-Christian tradition, creation implied order arising from chaos, the light of darkness. In the beginning, God created heaven and earth, and the earth was informed and empty, and darkness covered the face of the abyss. And the Spirit of God moved on the face of the waters. And God said, "The light is made." A cathedral was the medieval equivalent of a giant particle accelerator. France in the 14th century proportionally spent more on cathedrals than the United States to send a man to the moon in the 60s. As spacecraft or particle accelerators, the cathedrals promoted the existing technology to the limit. This cathedral, that of Beauvais, in France, the one with the highest height in the world, collapsed twice and had to be rebuilt. Often to religion and science is presented as if they were opponents. But science owes a lot to religion. Modern science begins in the Renaissance with the rediscovery of the ancient Greek idea that nature is rationally understandable. But from the beginning, science incorporated another equally important idea, that the universe is actually a universe, a single system governed by a simple series of laws. Lations took that idea of the Judeo-Christian and Muslim belief in one God. Perform me to read a prayer. It is the Lord our God, great is his power and his wisdom is infinite. Skirts, glorifying him sun and moon, and you planets, because of him, with him and in him, there are all things, all perception and all knowledge. This prayer was written in the 17th century not by a priest, but by an astronomer, Kepler, who discovered the laws that govern the movement of the planets. The founders of modern science, Kepler and Copernicus and Sam Newton, and even Galileo despite all his problems with the church, were deeply religious men. I do not say that you have to believe in God to be a scientist. Athens and agnostics have been Nobel Prizes, as they have been Christian and Jews and Hindu and Muslims and Buddhists. But modern scientific research, especially uniform theory, this stig of the triumph of the ancient belief that all creation could be governed by a unique and elegantly beautiful principle. The priests of the Middle Ages built their stone cathedrals, but they did it to express ideas. The stones can only reach a certain height, but the ideas can cross the universe. Wilson Hall, headquarters of the Fermilab particle accelerator, was designed in part based on the Beauvais Cathedral. Robert Wilson, the physicist and sculptor who built Fermilab, said he felt impressed by what he called curious similarities between cathedrals and accelerators, as the cathedrals were reaching impressive heights in space and the accelerators reach unprecedented energy levels, and the way in which both embody what Wilson called a last expression. But whatever the similarities between Fermilab and the Beauvais Cathedral, there are also deep differences between them, and between science and religion. The scientific theories are limited by the experimental results. Fermilab is being supercharged to increasingly high energies to subject new theories to increasingly rigorous tests. The men and women who built Fermilab share the scientific belief that the universe is rationally understandable and built this machine to test their faith. Broken Symmetry, a Wilson sculpture that rises at the entrance of Fermilab, expresses one of the beliefs of modern physics, that the universe could have begun in a state of perfect symmetry. Theories say that matter was condensed from energy when the primitive universe began to expand and cool, that the forms arose from the masses reports such as ice crystals when a lake freezed. That is, and m. Mathematical symmetries that uniform theories have exposed as the foundation of natural law are more subtle and complex than those of snowflakes, but the principle is the same. They imply that we live in a crystallized universe of broken symmetries. Thanks for seeing the video. Perfect symmetry can be beautiful, but also sterile. A symmetrically perfect space means nothing. As soon as an object is introduced in that space, symmetry is broken, creating the meaning of the location. There is a place where the object is and another where it is not. And from there we reveal all the geometry of the space as we know it. Symmetrically perfect time means that nothing can happen. At the time we have an event, symmetry is broken and time begins to flow in a given direction. We live in a universe in which objects and events abound, which means that it is imperfect, that the symmetries in the universe in which we live are broken. It could be that we owe the same origin of our universe to the imperfection that involves the breakage of absolute symmetry, of the absolute emptiness. There is a theory for this approach. It is called the emptiness of Genesis and suggests that the universe began as a single particle that arose from an absolute void. By strange that it seems, this idea does not violate any of the known physical laws. We have seen as real particles constantly arise from a void and fall again in non-existence. There seems to be limit for the size and longevity of the particles created in this way. It is possible that there could have been an absolute nothing from which a particle so powerful arose that it could have given rise to the entire universe. It is not very likely. But it should only have happened once. The emptiness theory of Genesis is a new idea and nobody knows if it is true or not, but satisfies two of the criteria of a solid scientific theory. It seems so strange that it is absurd. And as the universe itself, the more it is known, the more beautiful it seems. Nothing could have emerged the spark of Genesis. While the universe expanded and cooled, the darkness descended. Then the light was born with the formation of the first stars. Each star is a nuclear oven where matter is introduced by releasing a bit of the energy inherited from the first fireball. Thank you to imperfection. To the broken symmetries that caused the differences between the particles and the forces, the atoms could join the molecules. And the molecules bind to form life. And life gives way to thought. And thought generates theories about the creation of the universe. There is nothing more dead than an equation. You write an equation in a tile on the ground and in another tile you write another equation that you think it can be a better description of the universe. And you continue writing equations with the hope of finding an equation better and better to explain what the universe is and does. And when you have finished with all the tiles, and you have to leave the room, move your magic wand and order to the equations that do not get wings and will fly. And however the universe flies. It has a life that the equations do not have. Yes, a life, and it is the same life in which we are immersed. The great explosion has emerged a non-chaotic system. Otherwise, the cause-effect relationship that exists will be impossible. So the design that one sees in the universe can be as natural as the result of the differential equations. But the mystery is, why is the world likely to be described in terms of differential equations? And that is the answer that physics gives us. Always, students have been baffled with the formulas that great scientists have discovered, but the universe works based on those formulas. So the universe we observe is not a casual phenomenon. I find it loving nature and work to preserve the level of baskets and birds and other animals and habitats in general, which is very related to being interested in you can see the laws of nature, as nature operates, for example, from the point of view of physics, of fundamental physics. For me all this is part of the same whole, the beauty that nature shows in some wild creatures. As the giant coaches in Amazon Peru. That beauty for me is related to the beauty we appreciate when we study the fundamental laws of physics. They are all different means that have the nature of showing us their beauty. Since he was 13 or 14, I have always wanted to know. How did the universe work and why? And why is it as it is? Now, I have a slight idea how the universe works. But I still really understand why. Einstein used to say that the most incomprehensible the universe is that it is understandable. It is an old enigma. What is in the human mind so in line with the universe that we are able to understand anything about the functioning of nature to the greatest of the scales? It is a philosophical issue, I suppose, but science has been able to provide us with a small portion of the answer. When we study the subatomic particles and the stars and galaxies, we get everywhere that the universe is all of one piece and that began as a single seed smaller than an atom. And in a real sense, you and I were there. Each portion of matter and energy of our blood and our bones and the nerve centers of our thoughts can draw their lineage back until reaching the origin of the universe. The natural laws that were fragmented and multiplied as the universe expanded and cooled continues to operate today in the beats of our hearts and in the trajectories of the stars. As the Quran says, the universe is as compact as the veins of our necks. The evolution of the universe continues, not around us but within us. Our thoughts and feelings are, after all, part of the universe. Its history is also our history. Thank you to watch the video.